Have you ever really thought about what makes something strong? I mean, why is it that some materials can stretch for days while others just snap? Well, in the next few minutes, we're going to break down the science behind all of it. Let's dive in.
You know this phenomenon. It's something you've probably seen a million times. You take a rubber band, you give it a good pull, you let go, and snap, it's right back to how it was. But if you do the exact same thing to a plastic grocery bag, it just stays stretched out, all sad and deformed. So what is actually going on there? What's the real difference?
To get to the bottom of this, we've got to learn to speak the language that engineers use. And really, it just boils down to two key ideas, two essential words. If you can get these two words, you'll unlock the entire story of what happens to a material when you pull on it.
All right, first up is stress. Now, imagine you're pulling a rope in a game of tug-of-war. Stress isn't just about how hard you're pulling. It's that force spread out over the thickness of the rope. You can think of it as the pressure that's building up inside the material, fighting back against your pull. Okay, so for every action, there's a reaction, right? In our story, that reaction is called strain. If stress is the pull you're putting on the material, strain is just how much it actually stretches out in response. It's basically the change in length. That's it.
So let's just nail this down. It's super simple. Stress is the cause. It's the force we're applying. And strain is the effect. It's the stretch that happens because of that force. You have to remember this relationship because it is the absolute key to everything that comes next.
Now this is where it gets really cool. Engineers can take this whole relationship and plot it on one incredibly powerful graph. It's called the stress-strain curve. And this one curve can literally tell you the entire life story of a material, from the very first tug all the way to its final dramatic break.
So, the story begins in what's called the elastic region. This is the first part of the graph. We start to apply a little bit of stress and the material starts to stretch. That's the strain. But here's the key. If we let go, it snaps right back to its original shape. No harm done. This is our rubber band in action.
But what happens if we keep pulling? Well, we reach this really critical moment on the graph. It's called the yield point. You can think of this as the point of no return. The second we go past this point, any stretching we do from here on out is going to be permanent. There's no going back.
So once we've crossed that line, we enter a whole new phase, the plastic region. Deep down, on a molecular level, the material's internal structure is literally rearranging itself. The long-chain molecules are sliding past each other for good. The damage is done, and yep, you guessed it, this is our stretched-out plastic bag.
Now, if we still keep adding more stress, we eventually push the material to its absolute limit. We reach the end of the line. This is the breaking point. The material has taken all the abuse it can handle, it fails, it fractures, and its story is over.
Okay, so it is absolutely critical to understand the difference between these 2 points. At the yield point, the material is permanently changed, but it's still in one piece. At the breaking point, it's game over. The material actually fails. It's also worth noting that up until that yield point, things are pretty predictable. They follow a rule called Hooke's law. But after that point, all bets are off.
So we have this amazing story that the graph tells us, right? But how do scientists and engineers turn that story into useful, hard numbers? Well, they use a set of key metrics that act like a performance report for the material.
These are some of the vital stats. Think of them like the stats on the back of an athlete's trading card. Each one tells us something unique and important about the material's character, how strong it is, how stiff, how tough. Let's just touch on a couple of the most important ones. Tenacity is a huge one. This is simply the highest peak on that stress-strain curve. It tells you the absolute maximum stress that a material can possibly handle before it breaks. When you want to know how strong something is, tenacity's your number. Next up, let's talk about the initial modulus. Don't let the name scare you. It's just the slope of the curve right at the very beginning. If that line is super steep, it means you have a high modulus. The material is very stiff and it really resists being stretched. If the slope is more shallow, the material is way more flexible.
So how do we even get this data to draw the curve in the first place? It's not like someone is just sketching it out. No, engineers use these incredibly precise testing machines, and there are 2 main ways they do it. The first method is called constant rate of loading, or CRL. Here, they add weight at a nice steady rate, and they just measure how much the material stretches. The other method is called constant rate of elongation, or CRE.
With this one, they stretch the material at a steady speed and measure how much force it takes to do it. It's a subtle difference, but super important. One adds weight and measures stretch, the other stretches and measures the force.
Okay, I know. Graphs, metrics, test methods. But why does any of this actually matter in the real world? Well, it matters because these properties, they decide everything. They dictate why we use certain materials for certain jobs, from the shirt on your back to the bridge you drive over.
Just think about it for a second. If you're making a parachute or a climbing rope, you better believe you need high tenacity, right? It just cannot break. What about a car's crumple zone? For that, you want something that can absorb a massive amount of energy before it fails. And for a wrinkle-resistant shirt, you're looking for a high initial modulus to keep it stiff and crisp.
So the next time you stretch a rubber band or pull on a rope, you'll know about the invisible story playing out inside it, all along that stress-strain curve. Which brings me to one final thought for you. Based on everything we've talked about, how would you go about designing the perfect material for a parachute cord compared to the perfect material for a car bumper? The answers are completely different, and they all lie in how you shape that curve.